Up to this point, we define the 6 trig functions based off of either the unit circle or a right triangle. And what we're going to talk about today is how we can define these functions for any angle. And I'd like to describe this process in example 1. For starters, in this picture down here, I have the point 4, 3 that's sitting right here. And this point creates an angle theta if we draw a line that goes back to 0, 0. So this will be the terminal side of the angle. And it creates theta with the positive x-axis. One thing to note is that this circle that I have drawn here, I'm just sort of outlining it as a guide. This is definitely not a unit circle. In fact, the radius of this circle is 5 because to go from here out to the edge is a distance of 5. That's also true for this distance here. So I'm going to label the length of this side, this radius, as 5. So all that being said, if we're going to start by evaluating the 6 trig functions for this angle theta, I'll start with sine. What's sine of theta? If this were just a unit circle, that is a circle of radius 1, the answer would be the y-coordinate. But this is not a unit circle. In fact, the radius is 5. But there's still a way that you can figure out the value of sine of theta. You could actually draw in a right triangle and then use what we know about right triangle trigonometry to determine the value of sine of theta. Sine of theta is the opposite side, its length, over the hypotenuse. So what is this length? The length of the opposite side is 3, because that's the y value. That's how far you go up. So in fact, sine of theta is equal to 3/5. So what's cosine of theta? This is nothing new here. We can again use this right triangle to figure it out. Cosine of this angle is going to be the adjacent side over the hypotenuse, and the hypotenuse is 5. What's the length of this side? Well, that's determined by the x-coordinate of this point, which is 4. So cosine of theta is 4/5. So what's going on here? In general, if we have a circle of any radius, and I'll call that radius r, in this case r was equal to 5, if you want to know sine of theta, it is the y-coordinate divided by the radius of the circle. If you want to know cosine, that's going to be the x-coordinate divided by the radius of the circle. All we're adding here is, since we don't have a unit circle, since the radius isn't 1, we now have to divide by that radius to determine the values of sine and cosine. So continuing in this idea, what's tangent of theta? Well, off of this right triangle, that would be the opposite over the adjacent, so I know that's going to be equal to 3/4. Now, in terms of coordinates, that's going to be the y value divided by the x value. Now this leaves us with 3 other trig functions, that is cosecant of theta, that's the reciprocal of sine, secant of theta, that's the reciprocal of cosine, and then cotangent of theta will be our reciprocal of tangent. Once you know these 3 values, it's pretty easy to get these. If you have a fraction, you can flip the fraction. That's what it means to be a reciprocal of a function that appears here. So for cosecant of theta, I look to this fraction and I flip it, and the answer is going to be 5/3. Same idea for secant. I look here, I check out this fraction, and I flip it to get 5/4. And then for tangent, again, here I have, well, the fraction's 3/4, so its reciprocal will be 4/3. Of course, you could generalize this. That's the same thing as just flipping the 3 fractions that I have put over here. So if y over r is equal to sine of theta, if I flip that fraction, I get r over y. For secant, I get r over x. And for cotangent, I get x over y. So what's nice about this, in terms of defining things in terms of the coordinates, not much has changed when we're working in the first quadrant. It's identical to just drawing a right triangle and then getting your answers for these 6 trig functions. However, as you move this point to other quadrants, like the second, the third, or the fourth quadrants, well, now your x and your y values might change sign. Like over here, well, the x coordinates are negative. And down here, your y coordinates, for example, are negative. So you can use these definitions to determine these 6 trig functions, and knowing the quadrant that it's located in will tell you if the value of sine or cosine or tangent are positive or negative. Let's use the definitions that we defined in example 1 here in example 2. So similar idea. Here we have a point 9, -6. That's this point here in blue. And this point creates an angle. So if I start here and I draw a line going out to that point, you could think of this as rotating by this angle theta here. So for this angle theta, what is sine, cosine, and so on? What are those things equal to? The definitions that we came up with on the previous slide were, okay, well, sine of this angle, we're going to define it to be, the y coordinate over the radius. Cosine of theta was equal to the x value over the radius of this circle, the radius being the distance from the center out to the point. And then tangent of theta was equal to the y value over x. And then once you have these 3 things, you can flip all of them to determine, well, cosecant is going to be the reciprocal of sine, so you get r over y. Secant will be the reciprocal of cosine, so that's r over x. And then lastly, cotangent is going to be equal to x over y. I want to figure out these 6 functions. All right, well, if we start with sine, the good news is I know the y coordinate is -6, so that's going to be the number that goes here. That's perfect. But I don't know the radius of this circle. Like, what is the distance from the center out to this point, which I'm calling r? What is that equal to? You need to know that. One way you can figure this out is actually by using the Pythagorean Theorem. So this coordinate here has a y value of 9. So that means you'd go here, you'd go out to 9. Then, so this distance is 9. Then in terms of distance, you're going from here down to here. Now it's at y equals -6, but the distance of it itself is 6. And using these numbers and the radius and the Pythagorean theorem, I know that 9 squared plus 6 squared is equal to r squared. So that's this side squared plus this side squared is equal to this side squared. Let's simplify it and see what r is equal to. 9 squared is 81. 6 squared is 36. If I add these numbers together, I get 117 is equal to r squared. And then by taking the square root of both sides, I get the square root of 117 is equal to r. Technically, this process gives you a plus or minus on the side. Here we're talking about a distance, and so we'll leave it as the positive answer. I didn't leave enough space to completely simplify this value here, but it turns out there are perfect squares within 117, meaning we can reduce this square root a little bit. So I guess I'll put that above the circle that I've drawn. But if you're taking the square root of 117, just to be careful, I divided 117 by perfect squares, like by 4, 9, 16, and so on, to see if any of those numbers went into it. So I'm even trying this on my calculator right now. Okay, when I divide 117 by 9, I get 13. This means the square root of 117 is really equal to the square root of 9 times 13. Those are equivalent. But the reason that this is important to divide it by a perfect square is if you have a product, you can take the square root of the products separately. If you take the square root of 13, okay, that can't be simplified. It would just stay 13. However, the square root of 9 is 3. So this thing simplifies to 3 square root of 13. So this number and this number, if you type them into a calculator, give you the same thing. However, this won't be considered more simplified just because the number underneath the square root has been reduced. So I'm actually going to use this number to represent the radius of the circle, only because it's going to give me a more simplified answer. So we'll see how that works over here. Okay, we can now figure out these 6 trig functions. I'm going to start with sine of theta. Sine of theta is defined to be the y value divided by the radius of the circle. Well, the y value is -6, so I'm going to plug that in. And the radius is 3 root 13. And I see some stuff can cancel. 3 goes into itself once, it goes into 6 twice. So more simplified, this is going to be -2 over the square root of 13. And lastly, there's one other thing that you can do. We can rationalize the denominator by multiplying the top and bottom by the square root of 13. It's customary to not leave a square root in the denominator, so here we're multiplying by 1. If we multiply the denominators together, you are just left with 13 with no square root, and in the numerator we have -2 times root 13. I think I'm going to run out of room, so I'll just put that up here. This is -2 root 13 divided by 13. Technically, this thing would be considered our completely simplified answer. But just to recap, step 1 was I thought about where the point was located. I know that there's some circle that goes through this point, and I was like, well, what's the radius of that circle? And then we figured that out and simplified it. Sine is defined to be the y value divided by the radius of the circle, and that reduced down to this number here. The important thing about this definition is that sine took on a negative value, and that was completely determined by the y-coordinate. So as a point rotates around the circle, its location will tell you if the trig function will be positive or negative. Here, we have a negative y value, and therefore our answer was negative. Let's do the same thing for cosine. I think this will be pretty similar. For cosine, okay, it's going to be the x-coordinate, which is 9, divided by the radius, which is 3 root 13. Here, 3 again can go into itself once, it can go into 9 3 times. So that takes me to 3 over root 13. I again can rationalize the denominator by multiplying the top and bottom by the square root of 13. And when I do this, I get 3 root 13 over 13. And that would be my final answer, and I can't simplify that any further. Notice that cosine is positive, and that's because the x-coordinate was positive. All right, so what about tangent? All right, so for tangent, okay, that's defined to be the y-coordinate divided by the x-coordinate. So that's actually kind of nice here. I don't have to deal with the radius of the circle whatsoever. So here the y-coordinate is -6, and the x-coordinate is 9. And if I simplify this, this is going to be -2/3. We cannot simplify that anymore, so that would be the final answer. Now, to complete this question, we just need these other 3 trig functions. And hopefully with all of the work that we have written up here, there isn't too much left to do. I know we can get these 3 values merely by flipping fractions that appear up here. So we can start with anyone that we like. Here, sine of theta, its reciprocal is cosecant of theta. That would mean you could flip this fraction. Now, if you flip that, it'll put a square root back into the denominator, and that means you have to rationalize the denominator again. I think it would be better to take something that it is equivalent to, which when we did this process, we saw that sine of theta was equal to -2 divided by root 13. It's actually faster to flip this fraction here because you won't have to rationalize the denominator when you're done. This means the answer for cosecant of theta is -√13 over 2. And that came directly from looking at this fraction, which was equal to sine of theta, and I inverted it. I'll do the same thing for secant of theta. Now that technically would be the reciprocal of this. However, it'd make more sense to flip this fraction. And so my answer is really going to be root 13 over 3. No other work required. And for cotangent, again, I'll go to the most simplified fraction, this one here. If I flip it, I get negative 3 over 2. So these are the 6 values for these 6 trig functions. In example 3, let's try a similar problem just from a slightly different perspective. Okay, this time, we're actually given one of the trig functions, sine of theta is equal to 8 over 17. We are also told that theta is in the second quadrant, and using just those two things, can we find the exact values for the remaining 5 trig functions? Okay, since theta is in the second quadrant, that means we're starting here, rotating, somewhere over here. And sine of theta, let me write this off to the side. Sine of theta is equal to 8 over 17. Now the 8 on the top represents the y value of some point, and 17 represents how far we are from the origin. So this is not going to be an exact picture, but as a guide, if I start here and I go into the second quadrant, a distance of 17, just it's not perfect. I'll say that's the distance of 17. Okay, the y value of this coordinate must be 8. All right, so I've labeled all of my information in this picture. Maybe just for emphasis, I'll add that. Okay, this is the angle theta. Let's say you want to figure out what cosine of theta is equal to. What's that? Well, we defined it to be the x-coordinate of that point over r, the radius. Well, we know one of those things. I know that r is equal to 17. That's the distance from the origin. I just don't know what the x-coordinate of this point is. But we can figure it out. We can figure it out by setting up a triangle. So a right triangle. We need to label the sides of it. Well, this one's already 17. The length of this side is the y-coordinate, that is the height, so that is 8. And then, well, I just don't know what this side is equal to. And I guess I'll call it x, since it would in some way represent the x-coordinate of this point, how far you traveled in this direction. Okay, so the Pythagorean theorem states that if we square x and we square 8 is equal to 17 squared. All right, let's simplify this out. So x squared plus, okay, that's 64. Now if we square 17, we get 289. I'll subtract 64 from both sides, and we get that x. X squared is equal to 225. And if we're looking to solve for x, you can take the square root of both sides. Okay, so here x is equal to, and if we take the square root, I think that's 15, and it is. Okay, but here we have to be careful. This distance, if we think of this as a distance, certainly its length is going to be 15. Now, this 15 is also supposed to represent the x-coordinate of this point. And if you're going in this direction, this x-coordinate should take on a negative value. So I'm just going to add here that, okay, this is really x is equal to negative 15 if we're thinking about x as a coordinate. If this were a distance, great, the answer is 15. But the x-coordinate here would be, okay, we're at negative 15. Well, all that being said, I can now put that information back into cosine, and we get negative 15 over 17. Great. We were given sine, and we used that to solve for cosine. And I did that by drawing a figure, just as a guide. I labeled the information on a right triangle that came from sine. I solved for the remaining part, which was this side, and that gave me cosine by definition. All right, so, well, what about tangent of theta? Okay, so tangent is going to be the y value divided by the x value. So I'll write that definition back up here. And the y-coordinate is 8, and the x-coordinate is negative 15. You could leave it like this, or you could just put the negative in front of the fraction, but this is the value of tangent. The remaining trig functions are cosecant of theta, secant of theta, and cotangent of theta. Okay, these are the reciprocals of these three fractions, respectively. So starting with sine of theta, if I flip this fraction, I get 17 over 8. For secant, I'm going to flip this fraction, so I'll call the whole thing negative, but it's negative 17 over 15. And then for cotangent, same idea. I'm going to take the reciprocal of this fraction and call it negative 15 over 8. So these are the remaining 5 values for the other trig functions.